Okay, so next I'm going to show you how to do the same thing in CoppeliaSim, which is control partitioning. So in fact, we'll take one of the earlier example we took. We had a pendulum which we've modeled, and in this case, the initial position is going to be 0 for the pendulum, in which case it's going to be horizontal, and then our goal is to go to 90 degrees, which is going to make it vertically upright. Okay, and then we can generate reference motion using RML pause and RML step, which I've shown you earlier, but I'll reuse that code here, and then I'll show you how to do this using a naive PD controller and then using control partition. Okay, so before I actually start doing this in CoppeliaSim, I thought I should show you the corresponding MATLAB example. So we did this in MATLAB, and so here trying to do this thing in CoppeliaSim and compare it with MATLAB. So this was an example I showed in last class. So the pendulum goes upright, and then you can basically set the gains. So kp as hundreds and kd is 2 square root kp. So here, and then the main thing here was that we had a control, and that control was based on control partitioning. Okay, so my goal is to put this exactly the same formula in CoppeliaSim and show that it actually works the way it works in MATLAB, where I don't know the equations in CoppeliaSim, right? They are hidden from me, but since it's used the same, probably the same framework of deriving equations, we should have the same equations, so this should work. So we need to write all these equations, put them in CoppeliaSim in our torque, and then we should get it to work. So let's do that. Okay, so what I'm going to do here is I'm not going to build the pendulum. I already have built it in an earlier example, and I'm going to open that for you. So I have well, these two files. This was one of the tracking problem we did earlier. I think this was just a set point control. So if I run this, you can see that the pendulum is following a trajectory. Well, there's a reference and angle, which means that I've given a reference, and then it's tracking the reference. And so we can just probably look at the code here. The code here is, it's basically going from its current position, which we saw was vertical with horizontal, and it was going to 0, which I presume is the downward position. And then we have generated this trajectory using RML object and RML pause, and then we step through it using RML step. Okay, so the whole well, and then of course I just set the joint target position every single instant, which means that I used a PD control, and I'm sure the PD control is right here. Yeah, so I set this PD control. The P was 1, 0 for I, and D was 0. Okay, so there was just setting the target position. Here, what we're trying to do here, instead of setting the target position, we're actually putting out a torque. So we are going to use, set up a torque, and we are going to ensure that it follows that reference. So we'll copy a bulk of this code into our simulation, and we'll only change this control from set joint target position to set torque. Okay. Okay, so let's see how we do that. Okay, so what I did was I actually have another file, and this file uh, has, well, if you look at the script, there's nothing in the script. What I did for this file was I actually changed the joint angle such that if you see this is 0, that means this position is actually the 0 position. If you want to check that, you can put minus 90. And then you see it's downwards, so I set it in the right way. I have the MATLAB code set up, and then what I did was I set some of the parameters for the pendulum. So if you look at the pendulum, show dynamic properties, you'll see that I set the mass of the pendulum to be 1 kilogram, Okay, and that 1 kilogram is right in the middle of the pendulum, right? So if it's a, I believe it's a 1 meter long pendulum, so it's at 0.5, and then I set the x, y, z inertia as 0.5, and those inertia is always about the center of mass. So I'll use these numbers later on for control. Okay, so what I need to do now is basically set up uh, the trajectory first. And once I set up the trajectory, I just track that trajectory using a naive PD controller, which is probably the easier thing. And then I'll do control partitioning. So a lot of it is actually copy pasting the code from here. Okay, so let's just take this code, make a copy of this, put it in a text file. So here's my code. And then here in my new file, I'm going to modify this. So that's my pendulum. Okay, I don't need this. I need code this much. With the code. Okay, this is my code from uh, the other simulation where I did joint target position. Okay, let's start copying things here. So let me just copy this verbatim here. Okay, so let's see if this makes sense. There's graph. It's probably no graph. Just comment that for a second. Joint, uh, get joint position. That's fine. So the current position will read essentially 0. So that's fine. But I want it to go all the way to 90 degrees. So I do math dot pi divided by 2. So that's 90 degrees. And this is Maxwell acceleration jerk. Let's just see what it is right now. So that's set. Now let's go to the next part of this code in the actuation. So let me just copy this entire thing. Here, and then the final thing I need to copy is this, so it'll clear up memory. Okay, so this graph object doesn't exist. I need to create that. This will probably not work because I've not set the, so I set it to be quite doing position control. So let me just do that. So we're just getting it to work based on our earlier code and see if it works. So joint, let's go to dynamic properties. Here we motor enable, control loop enable. I believe we put 1. So let's just be 1. And let's see if this works now. Okay. That's pretty good. It's pretty robust code. I could just copy paste it, do minimum modifications. It worked. Okay, now we want to now change from target position to setting up the joints ourselves. Okay, so what I'm going to do is I'm going to go back to joint and stop it from setting this loop. Let me just set this to 0. This goes away, this goes away. Okay, so I'm going to set everything programmatically in the code. Okay, now first thing I need to set this to essentially do position control, the torque control for that. And I'm going to go and dig through the manual for the command, but the command is this. You basically take joint and you set the motor to be enabled. That basically sets it to velocity control. That's the first step. The second step is to actually set the torque here. So instead of setting the torque, this is just printing the torque. Let's skip this. We want to set the torque, instead of setting the joint target position, we want to set the torque. So we set torque equals whatever the kp times kd times whatever that is, we'll put it there. And then we need to say set torque. For that, I'm going to just copy the code which I developed some time back. So that code, I'm going to paste it here. And this is copied from an earlier code which I did in the class. I just need to set the joint handle, which in this case is going to be joint. and the torque is whatever I get over here. So once it's done, it should be all set, but I just need to basically put in the Kp and Kd. So let's just make up some Kp. So let's say Kp equals 1, Kd equals 0. Okay, now we need to give, I need to get the position and velocity. So again, position, I already have this piece here. So I can take that, paste it here. So that gives me the position. Let me call it angle actually. So it's much more, or theta if you like, theta. And then I need to get theta dot. Now theta dot, there is a call to float parameter to get it. So I'm just going to copy that from an earlier code also. So that was basically making this call float parameter, and it's the parameter sim dot joint float param velocity. This is in the manual, so we get the velocity. So let's just call it. Let me just move it here. That can we call that theta dot, right? So we got the position and velocity of the pendulum. Now let's go here and work on this. Now we need the reference. The reference, as we know, is this. It actually comes from here. The first value is the position. So first value. The second value is the velocity. So theta dot ref equals. The third value is the acceleration. So just copy that. Okay, so we got that. We don't need that acceleration, but we just save that anyway. So now we need to put the value for the error. So let's just call that see, theta minus theta ref, theta dot minus theta dot ref. So that's our naive PD control. So let's see how this works. See, I don't think I need this anymore. So let's close this to save, and then zoom this a little bit and keep it like this maybe, and run this. Okay, so it doesn't look like it's doing much. That's because the gains are too low, probably. Let's ramp that up. Okay, it seems looks still low. Let's make it go to 100. Okay, so now before I actually do this, it's always a good idea to show how the joint changes and how the reference changes. Right? Let's just do some more work before we actually start seeing the differences. So let's make a plot, add a graph, and in this case, one thing we want to add here is the joint position. So joint position is should be somewhere here, joint position, and that's a joint. Okay, so that's, we can call it theta, right? And then we need to create a new data stream. This is for the reference. Now unfortunately reference is not available here directly, so I need to make a user defined variable, user data, and then call it theta ref. I'll set this up in simulation in my code. So we did that. We'll change the color, so the theta is the reference. Let's change the color of the reference to be white. Okay, so there's a contrast and we can see it. And now let's go to the code, and then I uncommented this. So graph is that graph, that looks good. And then I need to set the theta ref. I should have set it somewhere here. Currently no. Okay, let's go down. I think I commented out here, right here. So this is going to be theta dot ref, and then I need to set, okay, I actually set it in degrees. I need to set it in degrees, otherwise that graph shows in degrees. So now maybe it will do a better job of showing it. So problem with the code. Invalid data stream. Let's see 48. 48.
I think you only have the theta on the graph and not the theta dot. The theta dot ref. I think the names are different.
Oh, I see.
Yeah.
So you're saying this will fix it. Okay. Okay, so you can see that the reference is actually growing and becomes 90, but you're sort of tracking it, but it's okay, then it goes crazy. So one thing to note is that this will always, one thing to remember with control partitioning is your reference always works till 90 degrees. After that, it will go all crazy. So you want to limit it. This is like, I cannot stress this more importantly. When you're working on hardware, always remember that your reference will always go up to the final position. It won't go beyond that. So beyond that, you might want it to either hold on to the position or kill the robot, which is really hard to do, right? Kill the controller. You could just keep the torque to be that value, whatever you get at the end, because it's going to stop. So you could do either of them. So what we can do is we can set this to so this is when it finishes. In this case, it's not going through this. I believe this will work. Let's see what happens. So here you can see it's sort of tracking it. Of course, I need to tune the PID. No, that didn't work. So I need to find that theta at the torque at the end and just hold it. I think what I can do is I can basically put that. Actually, you know what? Let me just kill the simulation or pause the simulation. The easiest way to stop it would be, okay, so it just stops. Let's see if that works first. So let's just get this to work first. Yeah, it stopped now, but you can see it's not perfectly tracking. Stop this. Okay, now it'll be, I don't have to zoom it or move the screen. Let's just change the gains to say 10 and see what happens. Slightly better. You don't see the fluctuations. That looks good instead of tracking. Initially, it's not that good. I mean, you can just play with this. It just turns out to be kind of hard to play with it. Right? You just have to keep tuning it. Okay. Now what we can do is let's just see if we can ramp up the. These are the Maxwell max acceleration max. This determines how fast the pendulum goes up. Let's just do it this way. Let's just choose the max well to be 1, right? This is 1. So let's call that max well. And then you can see max acceleration is 0.1 of max well. Okay, so let's call that max well, max acceleration, and then max jerk, you can see is 0.1 of max. Okay, so now we can just tune one number, right? We can just take Maxwell and everything be taken care of. So 1 we already saw. Let's make it 10. As you can see, the response will be faster. Okay, that's good, no problem. Let's ramp it up to 100. Okay, you can see there's an overshoot, and you can see the tracking has deteriorated slightly. Let's make it, I don't know if you go 1000. Let's just try 1000. Okay, that was a big overshoot. Okay, so it looks like it's going to start giving a poor response as I ramp up the speed. Okay, so let's now change to control partitioning. Okay, so this is going to be my PD control, which I will keep as one of the controllers. So this is part A. And let's do part B now. So the only thing I need to change here is this is my PD control. The reference and all remains the same for both. And now let's do B. control partitioning. So then this comments. Okay, so for control partitioning, I'm just going to use my MATLAB formula. So remember, this was my control partitioning formula. I'm just going to copy this right here. Okay, we don't need this. Okay, so I need to set this to, let's call it torque, and then we keep everything as it is. Now we need to define these terms. So M1 is the mass, which I saw was, well, here you can check it. It's basically 1 kilogram, one, right? Yeah, it's 1, and then 0.5 for the XYZ inertia. In this case, I'm only interested in the inertia about the Z axis, so 0.5. So let's just make it 0.5 for inertia. So mass is 1, inertia I1 is 0.5. Gravity is 9.81, and then L1. Now L1 is, in this case, in my simulation, L1 was the length of the pendulum, right? Because when you put 0.5, you get half the length, which is basically with the center of masses. So here I need to put it as 1, and you can check it here. If you go to view modify properties, you'll see that the length of the pendulum is actually 1. The 0.1 is the width and thickness. 0.1 is what I want. So put 1 there. And then I need to choose this Kp and Kd. So Kp1 and Kt1. Now, know that Kd is 2 times math dot square root Kd. Kp1. Okay, so I only need to set Kp. So let's just set it to 1. Start small. I think this formula is an older formula. I think I'm missing theta dot ref. Let me just put that here. Theta dot double dot ref. Kp C1 John. C1 is here, G1 is here, M1 is here. Okay, I think I'm all set. Few changes. Let's see if this works. Okay, there is a problem. I cannot call cosine, right? There's no cosine in this, so I need to define it as math.cosine. So let's do that. And then is there anything else? That looks good. Let's run this. Okay, bad argument to cosine, number expected got nil. Okay, line 67 looks right. Oh, there is no theta 1. There's no, I've not defined a theta 1, it's only theta. Let's get rid of this, and then it needs to be fixed everywhere. It should be theta ref. Theta. Oh, well, actually, this is a leftover formula from somewhere else. I need to modify this. This should be theta dot minus theta dot ref. I think it should work now. Start to set here. Okay, there's another problem here. 72. I did not close a bracket. It must be here. Okay, that closes this bracket. Okay, so you can see that just with the gain of 1, it actually did pretty well. There's some error. Let's ramp up the. By the way, this was, I put 1000. I should just start slow, right? Let's make it 10. Okay, and then make this Kp as 10. Okay, let's just do 1 first. See what happens. So you can see that the tracking is phenomenally good. It's bang on with just a gain of 1. Now, if we change that to 100, it's pretty good. And then we can keep ramping up. 1000. Okay, there is an error here. Now maybe I need to ramp up this one. Let's try 10. This is decreasing. The other issue which you face here is you want to be accurate with this. So I note that I've changed this to 10 ms and not kept it as 50 ms anymore, because I can't use a big gain if I use a low bandwidth for the integrator. So I'm going to ramp this up to 100. That's good. There's some problem here. So there's some point of time, the integrator will actually affect your results. So you can't just ramp it up. It's like 50. Yeah, that's pretty good. There's still an error. So that's like, if you're trying to go 90 degrees in 0.25 seconds, that's a really fast control. So yeah, this works, I guess, better than naive PD control. That's still there's an error here. Can check if there's something wrong here. I think it looks fine to me. It looks fine to me. Let's go slow. Yeah, that's better. That's going 90 degrees in 0.8 seconds, which is more realistic. But yeah, you can explore this by increasing the speed, and then going up with this. Okay, so that's it. So that's how you do control partitioning using CoppeliaSim. So I want to give a homework problem where you do this thing for two links. Uh, yeah, question. So did you get the inertia from the physical properties of the pendulum? Yes, I did. So what I did was I went to pendulum, show dynamic property, then I used 0.5. But you know what? Let's just try this. Let's just make it 2. And set it to 2. And now you should see the response won't be as good. It's no difference really, but it's actually moved. Uh, we can actually change it here. Change it to 2. Same problem. Okay. Ramp up the gain. Let's see what happens. Okay, that's better. So it just needed to ramp up the gains in that case. Yeah, so you can do this. In fact, we can check if this. What if I make this 0.1, 0.1? Okay, so now it's 2, which is the dominant one, which is in the z direction. Oh my god. So this happens when the inertias are badly scaled. One of them is too high and other is too low, and so it just moved off. You cannot have two small masses in this simulator because then it will fail. So I need to make it something reasonable, not close to 2 or of that order. Okay, so 4, 5, even 10 will be fine, I think, but you can't make it low. I believe that the response won't change. That's interesting. I didn't expect the response to change though. You try a slow speed. Yeah, that worked, sort of. Mesh is 2, length is 1. CG looks all fine. Yeah, I don't see a issue with anything here. If you see something, let me know. Okay. Okay, so I'll stop here. The what I wanted to do was I wanted to give you a double link pendulum, so 2 links, and I wanted to ask you to do the same thing for the double link pendulum. Okay, and I'll give you the start position, end position, all that. In that case, however, you will have to use what you'll need is, let's see, I do have a double pendulum here, code, double pendulum tracking. Then you have the control, which is this. So let me open that. So it's basically going to mirror this particular simulation. Here is 2 link pendulum. So this is the formula you'll be using to control a 2 link pendulum. Now you will have, instead of having a single number, you will have a matrix. You'll have theta dot ref, which will be 2 comma 1, and then you will have theta minus theta ref, which will be again 2 comma 1, and then c and g will be 2 comma 1, right? So basically you're dealing with matrices. Okay, now you could write your own matrix library and do this, but that's going to take too much time. Instead, what I suggest is, if you search for Lua matrix library, then you should go to this page, go to GitHub, and then basically what you need to do is you need to take this Lua, yeah, you need to take matrix.lua, this file, save it in the folder. So in this case, it's the folder. Okay, so I download it. It's basically in the folder where I'm working on. Here it is. And then I think you need to say import Lua, something like that. Let me see how to do this. You need to go here. Then I think you need to say import matrix dot Lua. You just see if that works. So if you look at that example, test, test, test matrix. Okay, so you need to do, my bad, you need to do this. So let's just go here, put that, and then where's the example? Okay, let's, so the way you define matrix is this. So if you want to define a 2 by 2 matrix, it's how you get it. So what I'm going to do is I'm going to print it here, and then if you, once you have a matrix, then you can use the matrix functions. So for example, if you use let me see, step back. Okay, so matrix start, if you want to display it, I think it's called show or print. It's called print. Yeah, matrix.print. This is how you show it to the screen. So matrix.print. So you go here and say matrix.print, and then you call mtx. Okay, so if everything works fine, you should see it printed. So let's just run this. Okay, this is saying there's a problem on line 7. Expected. Huh. You see something? Okay, this is the format. I think it's the same one. That looks good. And then
I don't know if this might be the problem, but when I used the matrix library, I saved it under the Lua folder in the program files directory. But I don't know if it will work if you just save it in your,
I see. I see.
yeah.
Oh, you mean if it's saved there? Okay. Let me see. MATLAB control point. Okay, so I've saved it here in the same folder where this is. Let me just see. I think I got it to work this way. Matrix, and then this is the example I did.
Okay.
Let's take this example and then put it right here. So this is a 2 by 2 matrix, 2 by 2 matrix. I print M1, M2, add them, and then print it. That's interesting because this is how I have it. Matrix.lua is the only place I have it, and then I have this file which I call which calls that. This is a different error. This is nothing to do with. That's weird. It does work here. It works no problem. So if you go here, it actually prints the matrices in this. So I did something wrong somewhere in my code. Let me just copy this part. Then go here. Go the same thing. Same line. Oh, it's a problem in matrix.lua. It's not here. There's something to do with my download. Let me just copy this file over here. Something here. Old. Okay. Yeah, I can see there's a difference. Yeah, this is a problem. This got corrupted when I downloaded it. Okay. So the right way to download is, I think, to download, use the zip format to download. So now if it should run fine. Let's just stop this and run this. Okay, so you can see it printed essentially 841683, there it is, minus 813521, and then 05. This is the addition of this. 8 minus 8 is 0, 4 plus 1 is 5, and so on. So yeah, this works. So if you put it this format, so I just keep this in this file so you can refer to it. But next time when you're downloading this file, what you want to do is you want to go here. Not this doesn't work. You should go to GitHub, and then don't download the way I downloaded, which is I took this and I just downloaded. That's a bad way to do it. Just take the code, download zip, go over here, open that, and then click the Lua file. But you can include it in the folder, but you can do what a Nestor did, which is you put it in one place, and then you don't have to keep a copy of it every time you use it. So in this case, I kept a copy of it here. It's MATLAB right here. Like this. Okay, so that's it. So I will give you a problem where you will be doing the simulating the double pendulum, right? And if you want to see what that looks like, this is how I got it to work. So my simulation work. It's just this is how it should work. If you get everything right. Okay, so I'll stop here.